Hello everybody, welcome to Canvas tutorial. This is our first lecture on organometallic chemistry, and in this lecture we will be discussing about 18 electron rule and ligand contribution. You know that this topic is very important from your examination point of view, and if you follow the previous year's question, then you can find that in every alternate year you can find one question from this topic. So okay, let's begin. Today we will learn that how to count electron or the valence electron, how to count the valence electron for organometallic compounds, and we will count the valence electron for these 15 questions. So before going to solve this kind of question, we are going to move on to our 18 electron rule and the ligand contribution topic. So before all, we are going to discuss the 18 electron rule, that what it says actually. It says that the number of valence electrons of any metal, okay, plus total number of electron contributed by all ligands. If this number is equals to 18, then it says that the organometallic compound or the complex is highly stable. So it is a condition for stability, and this is the 18 electron rule. Okay. So the question is that for which metal it is applicable. Mainly the metal is your transition metal. It is more pronounced in transition metals. Now the question is that why 18? You know that for main group elements they have a tendency to fulfill the octet. But what is the driving force of this 18 electron rule? What is the significance of the number 18? Now if you know the valence orbitals that actually take part in bond formation for transition metal, you will find that there is a ns orbital, where n is the principal quantum number, np orbital, and your n-1d orbital. Clear? For 3d block element, what you can see that 4s, 4p and 3d, these orbitals are involved. Okay, so what you can see that for bond formation these three orbitals are involved. So for s orbital there is one s orbital, for s there is one s orbital, for p there are 3 p orbital, and for d there are total 5 d orbitals. So overall how many total number of orbital is present? Total orbital is 9. So there is total 9 orbitals. Okay, among those 9 orbitals, what you can see that so between that 9 orbital, if we fill up with electron, so 9 into 2, overall 18 electron. So total this 18 electron is the maximum electron that can be filled, and this will give a fully filled configuration. So now it will acquire the 18 electron with the help of the ligands. So it has some valence electron and it will accept electron from ligand. Now it will try to fulfill its number 18. Okay, so it will try to get a fully filled configuration. Clear? So that is why the 18 electron complexes are more stable complexes. But not like that every compound will follow 18 electron. There is some exception which I am going to discuss, but most of the cases 18 electron complexes are stable. This is the message. Okay. Now the question arises that in which case that 18 electron rule is not applicable. In most of the cases what we find that for square planar complexes, okay, if you know the hybridization of the square planar complex, it is dsp2 hybridized or sp2d. Look at this, d orbital is involved in bond formation, s orbital, but between p orbital only 2 orbital is taking part in any bond formation. So for this case what I can say, for square planar geometry, in the square planar geometry, in the square planar geometry, one p orbital is of higher energy and cannot take part in bond formation. It is a general case. What happens generally, that one p orbital is of higher energy and it cannot take part in bond formation, and that is why now the available orbitals are, in earlier case what you see that there was total 9 orbitals, but now 1p is of greater energy, so now 8 orbital is there. So 8 into 2, it is 16 electron. So now it will try to fulfill its 16 electron structure, and that is why these complexes, most of the square planar complex, so what I can say, most of the square planar complex follow this 16 electron rule, or the 16 they will try to form the 16 electron complex in order to get the stability. Okay, so this is one case where the exception of 18 electron rule is observed. Now another case is that if you study this molecule of tungsten Me6. Now this is the alkyl group. Okay, this alkyl group contribute 1 electron. I will move on to that part, that which group will contribute how many electron. Anyway, so for the time being you should assume that, or you should remember that alkyl group contribute 1 electron. So now what happens, this tungsten has 6 electron. It is present in the chromium series. Now one thing is that you need to remember the d block element, the complete series of the d block element. So if you write, I am writing it in another ink, I am writing it in another color. Okay, so this is the total d block element. It is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Clear? So it is yttrium and lanthanum. Lanthanum is not transition metal, it is your lanthanide series. It is zirconium and hafnium. It is niobium and tantalum, molybdenum and tungsten. It is and rhenium, ruthenium, osmium, rhodium, IR, iridium, palladium, platinum, silver, gold, cadmium, mercury. I hope you already remember this thing. If you haven't, then write it for 50 times. I will not say you any trick. And I don't prefer to use those tricks or mnemonics. Most of the cases, this is a long series. Okay, this is a long sequence. In this case, the only thing you should do, that you should write it at least 50 to 60 times. Yes, you are right, 50 to 60 times I am saying. Once you write it, suppose in the morning, before starting your study, write the series once. Okay, so this is how you have to, you can think that you will write this series at least 2 times or 3 times daily. So if you follow this thing at least 5 to 6 days or 1 week, you will see that this series is completely in your hand. You need not worry about that. The sequence is completely, you know the sequence. So that is the point. So if you understand this thing, now what is the contribution? What is the valence electron? Now valence electron will be, for scandium series it is 3, now 4, 5, 6, 7, 8, 9, 10, 11 and 12. Okay. Now tungsten, look at this. This is a tungsten molecule, tungsten transition metal. Tungsten is present in chromium. So chromium, molybdenum, tungsten. So it is your 6 electron. So the valence electron is 6, and this methyl, 6 methyl gives you 6 electron. So overall it is 12 electron. It is not following the 18 electron, but it's a stable one. It's a stable one. You will find this kind of different molecules of titanium, okay, titanium, or your vanadium, which does not obey the 6 electron, which does not obey the 18 electron rule. Now the question is why? The rule is that if you focus on the left side of the D block elements in periodic table, what you can see that for the left side elements, there is lesser number of valence electron. Okay, there is lesser number of valence electron. Look at this, this titanium, okay, scandium, vanadium, zirconium, niobium, chromium. So they will have 3, 4, 5, 6. This is the number of valence electron present in their valence shell. So from here, what you can say, in order to get that 18 electron, the complete responsibility is on the ligands. Now what will happen, you need to understand the thing that more and more ligand should be there, should form the coordinate bond with the metal. Okay, so if more and more ligand is there, so the coordination number will automatically be high. Now the matter is that this transition metals are smaller in size, and the maximum coordination number that it can actually allow, it is the coordination number has a limit of 6. Okay, so it has a coordination number, limit is 6. So beyond the coordination number 6, this will not form a stable complex. So the point is that it has lesser valence electron and it cannot increase the coordination number beyond 6. So there is a limitation. So it cannot go beyond that limit. So what will happen? They have to satisfy in lower electron count. So not always they complete the 18 electron case, but they have to satisfy that and they have to form the stable complex because they have no other choice. Okay, that's why the left portion of that periodic table, you can see that it is due to the presence of lower number of valence electron. It will actually it cannot follow the 18 electron rule. So this is one case. Another case is that for platinum, there is a molecule on the platinum. Okay, there is a molecule, there is organometallic complex, platinum PCy3 whole 2. This complex, this cannot follow the 18 electron rule. Now if I draw the structure, you will find the reason that why it cannot follow this case. Okay, now I am drawing the structure. This Cy is your cyclohexyl group. This is the structure of cyclohexyl group. Now PCy3, that means one phosphorus is there. There is one cyclohexyl group. It is another cyclohexyl group. So 3 cyclohexyl group is there and pair of electron. It is donated to the platinum center. Okay. In this way, another this kind of PCy3 is there. Now this PCy3 ligand is nothing but your 2 electron contributor. Okay, so it will donate 2 electron. Now platinum is present in the nickel series, so it has a valence electron 10. So although it has more amount of valence electron, but now in order to fulfill the 18 electron, it requires 4 PCy3. It requires actually 4 PCy3 ligands. That is why it will be and in that case it will form the 18 electron. But it is so bulky. So here the reason is steric. So this PCy3 ligand, this ligand is very bulky ligand. So coordination number 4, even the coordination number 4 is not allowed. Okay. It is due to the bulkiness around this platinum, 4 PCy3 ligand cannot accommodate. So what will happen? They will form only there will be only 2 PCy3 ligand, and that means 2 into 2 4. So overall it is 14 electron, and it has to satisfy in this 14 electron, because unless it will be much more destabilized. But this compound is more or less stable and it is formed. Okay, so this is the case where the 18 electron rule is not obeyed. Clear? Now moving on to our another topic, hapticity of the ligand. And remember that this hapticity is valid for your organic ligands. Okay, organic ligands or organic compounds. So organic ligands, one example is your CP ligand. CP ligand is nothing but cyclopentadiene. diennyl anion. When this anion, it is an organic carbanion. This carbanion when acts as a ligand, then it is called the CP ligand. Now, if I draw the structure, then you will find that, okay, I am drawing the structure, negative charge. Now, what is the case? This negative charge can donate electron to the metal and it will form a bond between that, so it can form a complex. So, now the point is that how many center? Only one carbon center is donating. So, this is this hapticity. This hapticity is the number of donor atoms present in any organic ligand that donates electron simultaneously. Okay. So, simultaneously how many donor center is donating electron? Here in this case what you can say, only one center is donating electron. So, you can think that this is your hapto 1 CP. It has hapticity 1. There is another possibility. The possibility is this is a cyclopentadienyl CP ligand. The possibility is this will donate electron and this will also donate electron, pi bond. Once that pi bond is involved in donation or in ligand formation, what you can see, this one, this one, this one, these three centers. Now there are three centers are donating. So it is turned into your hapto 3. It is turned into your hapto 3 CP. Another possibility is that all the 2 pi bonds, so the 2 pi bonds along with this negative charge is donating. So here all the atoms are behaving as your donor center. Once this is the case, so it is your hapto 5 CP. It is your hapto 5 CP. So if nothing is mentioned, suppose you have got this kind of molecule CP2CO plus. In this way, what you can say, that this CP2, okay, CP2 is nothing but your hapto 5 CP. Maximum hapticity you will calculate. Okay, so this is the case. What is hapticity? Now you can take some more examples. Suppose I am taking this allyl. Now this allyl can donate from one center, so it can be hapto 1 allyl. It can be hapto 1 allyl. It can donate its pi electron as well. So you can think that it can behave as hapto 3 allyl. Okay, where this 3 center is donating electron. Okay, now matter is that what will be the ligand contribution. Now if you take a look at these ligands, okay, so this is the hydride ligand, halide ligand, hydroxyl, OR means it is alkoxide, NR2, NH2, alkyl, aryl, acyl ligand, SH, that means thiol. It is the analog of this NR2, okay. NR2, there could be PR2 ligand, PR2, PH2, phosphide ligand. These all contribute 1 electron. These all contribute 1 electron. Moving on to our 2 electron contributor, it could be your carbonyl, thiocarbonyl, it could be PR3, NR3, NH3, ammonia, phosphine, okay. Carbene, that means this molecule, dihydrogen, dinitrogen, this kind of bonding, it is common in the bioinorganic chemistry. In alkene, in Zeiss salt, you will find that this pi bond is donating, so it is also a 2 electron contributor. Alkyne, this pi bond is donating, so it is also a 2 electron contributor. So these are very famous ligands, and questions mainly comes from these ligands. So that is why I am giving you this chart. Now moving on to this carbine. Basically you can think that it is forming triple bond with the metal. So whatever, the carbine can contribute 3 electron. Now nitrosyl ligand is very interesting. Nitrosyl can present as a linear form and it can present as bent form. When it is linear, it has 3 electron. It is 3 electron contributor. When it is bent, it is 1 electron contributor. Now bridging ligand, this mu sign represents bridging, and 2 means it is the number of metal center. Sometimes you can find that only mu is there. because in bridging at least 2 metal centers should be present. So they sometimes will not give you mu2, only they in examination you will find mu Cl. If you find only mu Cl, okay, you need to understand that it is nothing but mu2 Cl. Okay, that means only 2 metal, at least 2 metal is present there. If greater than 2 metal is present, then they will mention. Whatever, you can find mu2 also. So this is the case when the bridging ligand is present. This carbonyl, okay, carbonyl was initially 2 electron donor. When it is bridging, it is also 2 electron donor. For the case of hydride, it is also 1 electron donor. No change in the case of bridging, but changes can happen in the case of halide. It was 1 electron donor, but here it is in bridging case it is 3 electron donor. In case of NR2, it was 1 electron donor for single metal. For 2 metal, there will be 3 electron donor. Alkyne was 2 electron donor. When 2 metal is there, that will be 4 electron donor. Now this mu4 pH, so they act as 4 electron donor, or the analog of pH like NH, ASH. You can think that this PR, okay, mu4 PR or mu4 NR, so they all are your 4 electron donor. They can act as the 4 electron donors. Okay, now moving on to our question. So this is the first question. Okay, now this is hapto 5. Now one thing is that what I didn't say, that for hapticities like hapto 1, hapto 2, hapto 3, whatever for these organic ligands, whatever the hapticity, that will be the number of donating electron or contributing electron. This is the simple case you need to remember. So this is a fantastic case that you don't need to understand all the thing, that what is hapticity or what is the structure of that ligand. If you forget the structure, only focusing on the hapticity, then only you can say that that will be the contribution, ligand contribution. So if it is hapto 3 Cp, 3 electron contributor, hapto 1, 1 electron contributor, hapto 2, 2 electron contributor, this is how it takes. Okay, so it is hapto 5 Cp means hapto 5 contributing 5 electron each. So it is 5 into 2, 10 electron. And iron contribute 8 electron. Okay, from this series you can say that it is 18 electron donor, total 18 electron donor. So this is nothing but your 18 electron complex. Now coming to our second question. Okay, okay, I'm removing this part. Now this hapto 5 means 5 electron, iron means 8 electron. Now carbonyl, each carbonyl is 2 electron donor, so there are 2 carbonyls, so 2 into 2, 4 electron. And chlorine, with a single metal, it is only 1 electron donor. So if you add them, it is 13, 17, 18 electron. It is 18 electron species. Okay, now moving on to our next question. We have just solved this one. It is 14 electron species. It is 14 electron, and WME6 we have said that we have already solved that it is your 12 electron species. Clear? Now coming to this part, Cp2 cobalt plus. Look at this, one positive charge is there. That is very important. In the first case, what you think that forget about the charge. So it is Cp. Cp means you should think that it is hapto 5. So it is 5 electron donor. There are 2 Cp, so 10 electron from 2 Cp ligand. And cobalt is 9 electron donor. Okay, now how many charges there? Now positive charge means there will be 1 electron lesser, so there will be 1 electron deficient, that species. So from here what you can say, you will subtract the positive charge. Suppose there is negative charge, in some complex there is negative charge, then you will add that charge. Clear? This is the case. So 10 plus 9 minus 8, it is 18 electron. So Cp2CO plus is your 18 electron. Remember, whenever positive charge will be there, you will subtract. Whenever negative charge is there, you will add. This is the case. Okay, moving on to this compound. This is a famous compound called Grubbs catalyst. In organic lecture, I will upload a separate video on Grubbs catalyst. It is used in the RCM, ring closing metathesis. Anyway, so now PCY3, PR3. This is nothing but this ligand. it is your 2 electron donor. Okay. Now chlorine is 1 electron donor, and this part, okay, this part is your carbene part, so it is your 2 electron donor. Once you identify that, now ruthenium is present in your iron, ruthenium, osmium. Okay, iron means 8 electron. Iron means 8 electron. So from here what you can say, this ruthenium means it is 8 electron, 2 chlorine atom, 2 into 1, 2 PCI3, 2 into 2, and 1 carbene, 2. So 8 plus 2 plus 4 plus 2, 10, 14, 15, 16 electron. It is 16 electron. 6. It is a 16 electron species. Okay. Now coming on to this one, DPPE. DPPE has a structure like this. This is a structure of DPPE. It has 2 electron. It has 2 electron. It's donating to the iridium. From here what you can say, that it is donating 4 electron. So DPPE is 4 electron contributor. So iridium is present in cobalt series, cobalt, rhodium and iridium, and cobalt means there will be 9 electron. So for iridium, 9 plus 2 DPPE, so 4 into 2, and there will be 1 positive charge. You will subtract the positive charge. So what you get, 9 plus 8, 17, 16 electron. You will get 16 electron. You will get 16 electron. Okay. Now moving on to this topic. Now look at this this question, hapto-6. Hapto-6 means it is 6 electron contributor. Carbonyl, 2 electron each, so there are 3 carbonyl, so 2 into 3. This is the case. And chromium, remember chromium, molybdenum, tungsten, so it is your 6 electron donor. So it is your 6 electron donor. As a result of that, what you get, it is 18 electron donor. Clear? Now next question. Now look at this. This is cobalt. Cobalt means it is 9 electron donor, 9 valence electron, and iron has 8 valence electron. Now how many cobalt? There are 2 cobalt, so it is 9 into 2, 18. Okay. Now there are 2 iron, so 2 iron is contributing 8 into 2, it is 16. Now 11 CO, each CO contributing 2 electrons, so it is 11 into 2, 22. Now mu4 means it is 4 electron. We have already seen that. This PR, okay, this is when there are 4 metal centers, so it is 4 electron donor. So for mu4 PPH2, so there are 2 mu4 PPH, so PPH, sorry, not PPH2. So these are nothing but your 4 electron donors. So it is nothing but 4 into 2, that means 8. So what is the total number of electron? It is so it is 64 electron. Clear? Now don't say that it is not 18, it is not following 18 electron, 16 electron abruptly high. Don't say like that. Look at this. How many metal centers are present? Is it only single metal? No. There are 2 cobalt and 2 iron. So total number of metal is 4. So if you divide 64 by 4, so it is 16. So it can behave as 16 electrons. So its stability is comparable to 16 electron species. Clear? So whatever the value you are getting, only rely on that value. Don't think that it is not 18, it is not 16, what will be? Because there are number of metal center is not 1, isn't it? So number of metal center is higher, so automatically the electron count will be higher. Okay. Now this is very important question. Tungsten is a 6 electron, 3 carbonyl, 3 into 2, 2 electron donor, each carbonyl donates 2 electron. Now SiMe3, okay, SiMe3 is nothing but your this kind of system, 3 methyl group is present. Okay, so this is comparable to Cr3. Cr3 means it is nothing but alkyl group. Only difference is that instead of carbon there is silicon. For CMe3, suppose there is CMe3, what you will say that it is a alkyl group, that means it is 1 electron donor. I said that. So SiMe3 will behave as alkyl group, so it will be plus 1. Now chlorine, it is 1 electron contributor. NMe3 is 2 electron contributor, so 2 into 2. So overall what you get, 6 plus 6 plus 2 plus 4, 12, 14, 18. So it is 18 electron. It is another 18 electron species. Okay. Now moving on to this question. Look at this. Iridium. Iridium means cobalt, rhodium, iridium. So 9 electron. It has 9 valence electron. 3 chlorine means 3 into 1, 1 electron each. PPH3, 2 electron donor. So 2 into 2. And AsPH2. Okay. It is nothing but like your NR2. NR2, PR2, ASR2. Remember, these all are your 1 electron donor. These all are your 1 electron donor. So there is one AsPH2, so that is 1 plus 1. And look at this. This is negative charge. Negative charge means you will add that. So this is added. So plus 1. So what you get? 9 plus 3 plus 4 plus 2. 12, 16, 18. So it is 18 electron species. Now moving on to this question. Now look at this. This is molybdenum. Molybdenum is in chromium group. Chromium means 6 electron. Okay, it has 6 electron. So valence electron 6. 3 carbonyl. So 3 into 2. And PCl2pH. If you take a look at this, it is nothing but your this PClClPH. So it is like your PR3. Okay, PR3. It behaves as PR3 ligand. So sorry, there will be hydrogen. Okay, it behaves as a PR3 ligand. So if it is true, so PR3 is 2 electron donor. We have said in the we have already seen in the list. So it is 2 electron donor. So 3 into 2. Okay. So 6 plus 6 plus 6, that will be 18 electron. Solved. Now moving on to this one. Cp is mentioned. That means you will see, you will think that it is hapto5. Hapto5 means it is donating 5 electron. Chromium 6 electron and 3 carbonyl means 6 electron. 3 into 2, 6. So it is nothing but your 17 electron. It is 17 electron species. Okay. Now moving on to this example. Look at this. This is your coordination sphere. Now don't don't bother about this thing, BF4 minus. Forget about this. Only focus on this positive charge. Okay. So this Cp means 5. Iron means 8 electron donor. Carbonyl means 2 electron donor. PPH3 means 2 electron donor. CF2 is 2 electron donor. And 1 positive charge, subtract 1. Understand? So it is 13, 15, 17, 19 minus 1, 18 electron. So this is your 18 electron. And moving on to our last question. These are 5 CO. So 5 into 2, 10 electron. Now chromium is 6 electron donor. And look at this part. So this is nothing but your carbene part. In carbene, what I said, that Cr2. Okay, this kind of bond formation will occur. So it is nothing but your 2 electron donor. So it is 2. So it is 18 electron. Okay. So this is your 18 electron species. So we have rapidly solved 15 questions. These are very easy. Just practice this 15 questions. Then only you will have the you will get the full concept about the 18 electron compound. In the next lecture, we will learn about the number of metal-metal bond calculation. So thank you. Happy learning.